In our previous session, we had discussed about the lift curve and pressure distribution curve. Let's start off with the wing introduction and high lift devices. Wing is a type of fin that produces lift while moving through air. Wing has streamlined cross-section of different airfoils. Aerodynamic forces act differently on different airfoils. Lift produced on the aircraft can be increased by using lift enhancement devices known as high lift devices. These are few of the high lift devices that are present on the wing, like leading edge flap, cups, slats, slots, and flaps. It is a fixed or movable component that can be deployed when required. There are two types of high lift devices: trailing edge high lift devices and leading edge high lift devices. The purpose of high lift devices to reduce takeoff and landing distance, reduces the stalling speed, makes use of the wing more efficiently in flight. Larger wing will produce more lift and reduce the distance speed required for takeoff and landing. These are few of the flaps that are plain flaps, split flaps, slotted flaps, and Fowler flaps. There are leading edge high lift devices like fixed slots, movable slot, leading edge flap, and leading edge cups. Low-speed airplanes versus high-speed airplanes. Low-speed airplanes have trailing edge high lift devices, like the seaplanes, where the aircraft speed is less than the speed of sound, that is, Mach is less than 1. High-speed airplanes have leading and trailing edge high lift devices, like the normal cargo airplane and passenger airplane, where the aircraft speed is more than the speed of sound, that is, Mach is greater than or equal to 1. Trailing edge flaps, we have plain flaps. Plain flap is simply a hinged portion of the trailing edge. It is hinged to the back of the wing and they pivot down when you extend them. However, they are fairly limited in the amount of lift they can create. This is because of air moves around the wing, it loses energy and starts to separate from the wing. It is simple to construct, produces good increase in CLmax, that is coefficient of lift maximum. It produces high drag, mainly used in low-speed aircraft. Effective angle of attack increases with extension of trailing edge. Split flaps. In a split flap, the lower surface hinges downwards while the upper surface remains either fixed on the wing or moves independently. They are located at the lower surface of the trailing edge. The upper surface is unaffected when lower flap is deployed. It produces more lift compared to plain flap at low angle of attack. It increases the lift at high angle of attack as upper camber is not increased but lower surface flow separation is delayed. Slotted and multiple slotted flaps. They have slots or gaps for faster moving of air from lower surface to flow over the upper surface. It delays the flow of separation on the upper surface. It produces great lift and less drag. They have complex construction depending on the multiple slots needed. Fowler flaps. The flap split and slides backward, then rotates down in creating one or more slots. This movement increases the movement's curvature, which increases chord and camber. The high lift Fowler's flap is located on the trailing edge of the aeroplane wing, which increases wing area, lift and drag. The flap often forms part of the upper surface of the wing similar to the plain flap or split flap, but upon extension it slides rearward before lowering. Fowler flaps always feature one or more flaps. It increases camber and surface area. It gives less drag because of the slots and reduction in thickness of chord ratio. Flaperons. These are specialized types of aircraft flight control surfaces that combine aspects of both flaps and ailerons. Flaperons respond to roll commands made by the pilot via the control wheel or stick in the same manner as conventional ailerons. The flaperons can also be symmetrically lowered to function similar to a dedicated set of flaps. The use of flaperons instead of separate flaps and ailerons can result in the overall reduction in the weight of the aircraft. Flaperons are often mounted well clear to the trailing edge of the wing to ensure undisturbed airflow across the flight control surfaces at low speed or at high angle of attack. This helps to reduce stall speed and improve low speed handling characteristics. Comparison of trailing edge flaps. These are the flaps that are present: plain flap, split flap, single slotted flap, double slotted flap, triple slotted flap, and Fowler flap. This is how they react to the coefficient of lift to the angle of attack. We can see that Fowler's flap has high coefficient of lift at low angle of attack and has a good performance when compared to the basic section, that is a plain flap or a normal airfoil without flaps. Slotted flap and split flap are also performing good, but when compared to all the other flaps present, Fowler flap is the best. Leading edge flap. We have Kruger flaps. Kruger flaps are mounted on the bottom surface of the wing and are hinged to their leading edge. Actuators extend the flap down and forward from the undersurface of the wing, thus increasing the wing camber, which in turn increases lift. Variable camber leading edge flaps are also called as variable camber Kruger flaps. The variable camber Kruger flap is one attempt to improve the chains of the deployed Kruger flap. The change of a simple Kruger flap and the main panel of the folding bull-nose Kruger flap are dedicated by the airfoil shape at the lower surface of the wing leading edge. The variable camber Kruger changes the main Kruger panel from the rigid to a flexible panel, which improves the airfoil shape of the Kruger dramatically and also improves the aerodynamic performance of the Kruger. It creates more camber and increases lift. It is more efficient than the normal Kruger flaps. Leading edge slot. Leading edge slots are a great way to increase the critical angle of attack, but they come with a high cruise performance penalty. To overcome the drag, engineers designed slats. Slats are same as slots except they open and close. In fact, slots are often called slats, though technically they are fixed slats. When air approaches the leading edge of an airfoil, it divides, some flowing over on the top of the wing and some flowing over the bottom. The spot where the airfoil splits is called the stagnation point. When the airfoil is at a low angle of attack, the stagnation point is on the leading edge. As you can see, it pushes the slat closed. When the airfoil is at high angle of attack, the stagnation point moves below the leading edge and behind the slat, where the air flowing up and over pushes the slat open. These are deployed to allow the wing to operate at a higher angle of attack, which reduces the speed. Takeoff and landing can be done in shorter distances. They decrease stall speed as coefficient of lift increases. Let us see how this happens. This is a graph plotted of coefficient of lift versus angle of attack with slat or leading edge flap, without slat or leading edge flap. This is the difference you get between the both. Let us see how. Let us start off with the equation of lift. We know that lift is equals to half rho V stall square CL max into S. Rearranging the equation, we get V stall is equals to root of L by rho S CL max. Since lift is equals to weight, we replace L by W. So we get V stall is equal to root of W by rho S CL max, which says that as CL max increases, the V stall decreases. Hence, we have proved. Hence, from here we can understand that without slat, coefficient of lift for a particular angle of attack is less, but when we use the slat or a leading edge flap, it increases to further delta CL maximum angle, and hence our performance can be improved. Comparison of leading edge slat with trailing edge. So here we have the airfoil, where we have plain airfoil, airfoil with flap, airfoil with slats, airfoil with slat and flap. Here we have the graph of CL versus angle of attack. The blue indicates the plain flap, which has a good lift to angle of attack ratio. But when we use airfoil with flap, it has better performance than the plain flap. But at the same time, when slats are used, it has a lesser performance than compared to flap, but it has a better performance than plain airfoil. And now when we see the airfoil with slats and flap, which is the orange color, it performs equally with airfoil with flaps, But due to the presence of slat, its performance increases move further with increase in angle of attack, and then we stalling taking place. So hence we use airfoil with slats and flaps for a better performance. I hope you would have understood today's session about high lift devices and wings. Let us start off with the airplane performance in our next lesson. Thank you.